Next we're going to do Enols and Enolates Part 2. We're going to take a look at a reaction called a conjugate addition, and it involves an alpha-beta unsaturated carbonyl. Now so far we've been just studying carbonyls on their own, aldehydes, ketones, esters, and the reactions they undergo. But when we have a double bond conjugated to that carbonyl, it imparts some new reactivity. Let's think about the resonance that this alpha-beta unsaturated carbonyl, also called an enone for short sometimes because it has both the alkene and the ketone. What kind of resonance would that enone have? Well, any carbonyl we know has resonance. So we know that this Lewis structure represents the structure and contributes to the overall hybrid of that enone. But the positive charge now is an allylic one, so there's an additional resonance form we can draw. That resonance is extended through the conjugated pi system, and we have a third resonance form. So overall, when you look at the reactivity of a alpha-beta unsaturated carbonyl, we know that we have the usual partial plus, partial minus of a carbonyl, but what we find is that that partial plus character, that electron deficiency, is extended down into this beta carbon as well. So we have two electrophilic sites in an alpha-beta unsaturated carbonyl. That means if a nucleophile is approaching this species, it has to decide between these two electrophilic sites on where to attack. Now, certain nucleophiles, such as hydride, Grignard, organolithium, these are very reactive nucleophiles, and they prefer to attack the carbonyl as usual. So if they see an alpha-beta unsaturated carbonyl, these nucleophiles are going to totally ignore the double bond, the carbon-carbon double bond, and go after the carbonyl as usual. We call this 1,2 addition because we had the nucleophile and the proton 1,2 to each other right next door. So in other words, they react like an ordinary ketone or aldehyde. But with the exception of hydride and Grignard, all other nucleophiles, when given an alpha-beta unsaturated carbonyl, will instead prefer to attack the beta carbon. We call this 1,4 addition or conjugate addition or Michael addition. We're going to see a reaction called the Michael reaction. So sometimes this is called the Michael addition. And what that looks like is the nucleophile doesn't attack the carbonyl, it attacks the beta carbon. And it could do that because we can break this pi bond and move it up, and then break this pi bond and move it up. So our intermediate looks something like this. Does this intermediate look familiar when we have a double bond and an O minus on the same carbon? This is an enolate. We're going to get an enolate intermediate when we use these when we do this conjugate addition. And when we do step 2 and we work this up, how would we protonate? Well, we're not going to protonate up on the oxygen because that would give us an unstable enol. Instead, we're going to protonate like we're going to react just like any enolate does. This lone pair is going to reform the carbonyl, and it's the alpha carbon that's going to get protonated. So there's our product. That's what the product looks like for a 1,4 addition. If you take a look at protonating at the oxygen, just for comparison's sake, that would not be a stable product because this would be an enol. So even if we tried to protonate in our workup on the oxygen, this would simply tautomerize back to the carbonyl. Okay, but this structure is nice because maybe you can see why it's described as a 1,4 addition. The nucleophile adds on the beta carbon, the proton effectively adds on the oxygen. Those are 1,4 from one another. So that's why we call this 1,4 addition versus 1,2 addition. And because all other nucleophiles other than hydride and Grignard prefer this 1,4 addition, that's what we're going to be spending some time on. Okay, what nucleophiles? Things like enolates, and also an organometallic reagent known as an organocuprate. So before we get into either of those examples, though, let's take a look at why it's okay for a nucleophile to add this alkene. we've never seen a nucleophile add to an alkene before. In fact, we've always seen alkenes as the nucleophiles themselves, and they go out and attack electrophiles. And so let's think about an ordinary alkene and try and do this nucleophilic addition. If a nucleophile tried to attack this alkene, we would get an intermediate like this, and that would not be a stable product. This is a very unstable C minus. There's nothing to help stabilize that negative charge, and so this would never happen. Nucleophiles do not attack ordinary alkenes. Okay, however, if that alkene is part of an alpha-beta unsaturated carbonyl system, let's think about that reaction. Same mechanism. Let's just add to the alkene to give this carbanion. And what's the difference now? This carbanion is now allylic to the carbonyl and is resonance stabilized. We come back to the recognizing the fact that we get this enolate intermediate. We get a resonance stabilized intermediate, and that's why, remember, we call this guy an enolate. Okay, and that's why in this case, nucleophilic addition is okay for an alpha-beta unsaturated alkene, but not for any other ordinary alkane. This is really a reaction that's unique to enones. So we call enones Michael acceptors, and they're not, and it doesn't have to be a ketone that's attached to that carbonyl in order to allow for a 1,4 or a conjugate addition. There are other so-called electrophilic alkenes that would accept attack by a nucleophile. We could have, instead of a ketone, we could have an ester, so any carbonyl-containing compound, or we could have a nitro or a cyano. Now we've seen the nitro and the cyano and the carbonyl all being grouped together before. We call these EWGs, or electron withdrawing groups. And what they all have in common is because of resonance, they all have partial positive character at this beta carbon, so a nucleophile would be attracted to that site, and they all would stabilize the carbanion intermediate that would result from nucleophilic attack. Okay, what do they all have in common? They all can withdraw electron density. The reason we're called electron withdrawing groups is they can withdraw electron density out of that double bond, putting a positive charge on that beta carbon. Any carbonyl can do it, a nitro can do it. So just looking at the resonance of the starting material, we can see right away why a nucleophile would be attracted to any of these species. That's why we call them electrophilic alkenes, right? So that means this is an electrophile, this is electrophilic, this is electrophilic. By attaching any electron withdrawing group to a double bond, we make that double bond a Michael acceptor, or something that is capable of undergoing a 1,4 addition or conjugate addition. So let's take a look at some of those reactions. One nucleophile that prefers to do this conjugate addition is called an organocuprate reagent. Cuprates have the formula R2CuLi, so there's two carbon groups attached to a copper metal. That's what makes them an organic organometallic reagent. And let's see an example of such a reagent. This is called dimethylcuprate, and like all organometallic reagents, it's a source of a nucleophilic carbon, a carbon as if that carbon, in this case a methyl group, had a lone pair and a negative charge. Now, because it's not ionic, it's actually coordinated to the metal, we put these around in quotes because to recognize that it's not ionic. But it's useful to draw it as a methyl minus because that's very handy in our nucleophile, in our mechanism. It also reminds us that it is definitely a nucleophilic species. So we have a nucleophile in step one. Where do we have an electrophile? Well, I know we always see a carbonyl and think it's electrophile, but we need to expand our definition now and see that when we have a conjugated and alpha-beta unsaturated carbonyl, that this is now going to be the electrophilic center of choice. And so what's going to happen is my methyl minus is going to attack here, break the pi bond, and break the pi bond. we break this pi bond, so it's going to give me an enolate intermediate. And I form, in this case, a new bond between the beta carbon and the organometallic carbon. And so in step 2, what's going to happen when we treat this with water, H3O plus, we do our workup. How are you going to protonate this intermediate? Well, it's a enolate, so it's the alpha carbon that's going to be reactive. So I'm going to use my O minus to reform the carbonyl and kick that pi bond out to protonate the alpha carbon. Okay, and this is what we saw in the overview slide of what a conjugate addition looks like, a 1,4 addition looks like. You break the pi bond of the carbon-carbon double bond, you add the nucleophile to the beta carbon, and you add a proton to the alpha carbon. That's going to be the overall pattern for when we do a conjugate addition or a 1,4 addition. So cuprates allow us to add a variety of carbon groups to the beta carbon. Let's take a little closer look at cuprates. How do we make them, and what kind of behavior can we expect from them? And also, what I want to point out is that the cuprates are nice to look at because these organometallic reagents are in contrast with the other organometallic reagents we studied up to this point. The other organometallic reagents, something like a phenylmagnesium bromide, a Grignard, if we did a Grignard reaction followed by H3O plus, that reacting with something like cyclohexanone would prefer to do a 1,2 addition. In other words, it attacks the carbonyl and gives an alcohol product. Okay, but instead, if I used a cuprate, if I used diphenyl cuprate, phenyl 2-CuLi followed by workup, then we would expect it to add to the 1,4 position because we have a partial positive here, we have a partial positive here, we have 2 electrophilic sites. So cuprates are very useful because they offer a complementary path to the other organometallic reagents, something that prefers to add 1,2 versus something that prefers to add 1,4. Okay, so where do cuprates come from? Well, they are actually prepared from organolithium reagents. Organolithium reagents are prepared from alkyl halides. Okay, so if we wanted to make this dimethyl cuprate, we'd start with methyl bromide or methyl iodide. We'd add in some lithium. And remember, lithium prefers to do a halogen metal exchange. So we end up, that's how we would form methyl lithium. And then we take 2 equivalents of methyl lithium and treat it with some copper salts, and we get out this organocuprate structure. We're always going to take 2 equivalents of the organolithium because we need 2 equivalents of this alkyl group or this carbon group to be associated with the copper. And one other interesting thing about the cuprates is that they can not only do a conjugate addition, but they will also do a coupling reaction with alkyl halides or even aryl halides, some other carbon groups, is that if you take this as your nucleophile and you take a halide as your electrophile, you can get those 2 to couple and get an alkane product. Okay, this is not true for a Grignard reaction. Grignards don't do SN2 reactions, and this is not an SN2. This is a metal coupling reaction. But this is very handy for synthesis, and again points to the difference in reactivities between a cuprate and an organolithium or a Grignard reagent. Now, the other nucleophile we'd like to see add, besides just an ordinary carbon group, is an enolate nucleophile. We call that reaction the Michael reaction when we do a 1,4 addition or a conjugate addition, where our nucleophile is an enolate and our electrophile is an enone. So let's take a look at an example of one of these. If we took this diester and treat it with sodium hydride is a good base. So that's going to deprotonate somewhere. Where can we deprotonate? There's only one place we could deprotonate in this case. It's the alpha carbon. So let's just make that an anion there. That's what generates the nucleophile in the first step. And in our second step now, we're adding in our alpha-beta unsaturated ester in this case. So that is our electrophile. And so let's see if we could draw a product. Let's see if we could draw the product that we expect, and then we'll take a look at the complete mechanism. Okay, we're going to form a new bond between this alpha carbon and this beta carbon, is the electrophilic carbon here. So let's redraw our enolate, have a new bond coming off from the alpha carbon, and then what is it going to be attached to? Remember, what does it look like when a nucleophile does a conjugate addition to an enone? You add the nucleophile to the beta carbon, and then you add a proton to the alpha carbon. And then we have our methyl ester group here. Okay, so this is the electrophile you added to the alpha carbon, and you could also think that this is the nucleophile that you've added to the beta carbon. So the Michael addition gets to be interesting, gets to be a little challenging because you have both a complex nucleophile and a complex electrophile, and you need to understand the behavior of both in order to accurately draw the product. Okay, let's see what that mechanism looks like. Our mechanism, we have our deprotonation of the alpha carbon. We use hydride in this case as our base. Any base will do. This is a one-way street, of course, because once we deprotonate, once you use hydride to deprotonate, you give off hydrogen gas. So this would be a way of 100% converting the diester to its enolate. And then in step 2, we bring in the electrophile. So we have our nucleophile, we have our electrophile, we have the alpha carbon attack the beta carbon, break the pi bond and move it up, break the pi bond and move it up. Eventually you want that extra electron density to be up on oxygen, so that's why we keep moving their electrons up there. And we can redraw. We also have to decide, because they're both kind of complicated, we have to decide which one do we keep right side up and which one do we have to turn around. And so I always find it easier to redraw the nucleophile, the enolate, standing upright. But then we have to move this guy down. So he's a CH2, single bond CH, double bond carbon, and then this carbon has an O- and an OCH3. O-, OCH3. Okay, so we just did our Michael addition, we just did our conjugate addition. Now we need to protonate. So that was step 2, and now step 3, we add in a proton source. We do a mild aqueous workup, and we're going to protonate. And here's where we have to be careful not to protonate on the oxygen. This is where doing the mechanism actually sometimes makes it a little harder than just trying to draw the product, because the mechanism might trip you up. Remember, we're going to be protonating our alpha carbon. So we reform our carbonyl, and it's the alpha carbon that gets protonated in our workup. So there's our new carbon-carbon bond to the beta carbon, and now this was a CH. Now that's how it becomes a CH2, single bond carbonyl, and then OCH3. And let's see, does that match what we guessed in the first place? It does. Our enolate now has a new group attached to the alpha carbon, and our enone, in this case it's an ester, our alpha beta unsaturated ester, now has a nucleophile added to the beta carbon and a proton added to the alpha carbon. Let's see one more example. How about if I mix these two reagents in the presence of some base? So rather than doing stepwise, let's just throw it all together. This is where, again, these problems can become challenging because you have to decide what's going to happen first. Okay, clearly I see that I have some base here though. Sodium methoxide is CH3O- because we have an Na+. So I have a base. I need to go somewhere and deprotonate. Where can I deprotonate? I'm going to find an alpha proton. I'm going to lose an alpha proton somewhere. Now, and this is where it starts to get a little complicated, because you have an alpha proton here and you have an alpha proton here. Now, I don't see a carbonyl, but remember, this nitro as an electron withdrawing group acts just like a carbonyl, even better. So this is an alpha proton just like this is. Okay, now how do I decide which one to go? Well, here's a hint I'm going to give you. As soon as you see your alpha beta unsaturated system here, you know that's going to be your electrophile. Okay, and you need to look elsewhere for a nucleophile to attack it. So it's going to be an electrophile at the beta carbon. I'm going to deprotonate over here at this alpha carbon. That's going to be my nucleophile. So now it's just a matter of drawing the product. Without going through a whole mechanism, let's see if we could draw the product. Let's start with our cyclohexenone. And if we want to do a conjugate addition, a Michael addition here, we break this pi bond, the alkene carbon gets added to. We add our nucleophile to the beta carbon. And what is the nucleophile that we're adding? Well, we know we're going to deprotonate this CH. So now it's just a carbon. And what else does it have attached? Methyl, methyl, nitro. CH3, CH3, NO2. And there's the product of our conjugate addition, extending to something beyond just ketones, aldehydes, and esters. Now there's another reaction called the Robinson annulation, and this one involves two reactions in tandem. It involves first a Michael reaction, so a 1,4 addition, a conjugate addition, and then it's followed by an intramolecular aldol. So if you know what a Michael reaction looks like, and you know what an aldol reaction looks like, then you should be able to do a Robinson annulation. And the Robinson is always going to involve, or most often involves, a substrate kind of like this. He's known as MVK. We need some kind of MVK derivative. That stands for methyl vinyl ketone. Okay, here's a ketone. I have a methyl group on one side, I have a vinyl group on another side, and you'll find that you'll have that component as part of your Robinson annulation. There might be additional things attached to it, but you need to have at least both those parts, and you'll see why in just a moment. Okay, the first thing that happens, we're going to react this in some base. It can also be acid catalyzed, but we'll take a look at the base one here. The first thing that happens is a Michael reaction. And a Michael reaction means I have a conjugate addition of an enolate. So like I said, every time you see an enone, you know that's going to be our electrophile. Our MVK is our electrophile here. So where is a nucleophile? Right over here we have our nucleophile, our alpha carbon. So the first thing that's going to happen is, let's bring them down here. The first thing we're going to have happen is a Michael, which means we're going to have a new group to this alpha carbon. We're going to have a CH2 and a CH. And I'm going to draw it around this way. I'm going to flip it over this way, keep it positioned as it was right here. Because now this is perfectly situated. We're not going to stop here because this intermediate structure is perfectly situated to do an aldol reaction. What does an aldol mean? It means we have an enolate, the alpha carbon of one attacking the carbonyl carbon of the other. So we have an alpha carbon right here. There's our nucleophile. And 1, 2, 3, 4, 5, 6 atoms away, very conveniently, we have an electrophile. We'll always end up 6 atoms away if we have a methylvinyl ketone sort of electrophile that we're adding to. So what happens is we now have an aldol reaction where we form a 6-membered ring, and it almost always involves the loss of water. When we have a cyclic structure like this, the loss of water is even more favorable, and so almost always we get this second reaction happening with loss of water. And so the pattern we get in our product is a cyclohexenone product. And a Robinson annulation will always be forming a 6-membered ring. Now notice we already started with a 6-membered ring, so that's why we have a second one now. We form a 6-membered ring, and it's always a cyclohexenone. It's got the double bond and the carbonyl. So let's see if we could do a mechanism for this. We're in base, so our first step is going to be deprotonate. We need to get started by doing the aldol reaction. So I'm going to deprotonate my alpha carbon. I'm using methoxide as my base. So step 1 is form the enolate. The enolate, of course, is a nucleophile, so we look around for an electrophile. That methylvinyl ketone is the other ingredient we had in our reaction. So that is our electrophile. So what does the nucleophile do? Alpha carbon to this beta carbon, that's the bond we're forming. Enolate attacks, breaks the pi bond, breaks the pi bond. Look at that, 4 arrows all in a single step of the mechanism. And this is the case now, again, when it comes to having errors, this is a very easy place to lose carbon. So let's check. We have a 1, 2, 3, 4 carbon chain, right, in methylvinyl ketone. So let's make sure we're adding a 1 single bond, 2 double bond, 3 O minus single bond, 4. You still need to have a 4 carbon chain that you're adding on top of the 6 carbons we already had. Okay, this is the number one most common place that we can accidentally lose carbons with our line drawings. So there's our conjugate addition, there's our Michael addition, and now we need to protonate to finish up this mechanism, this part of the mechanism. So let's bring in some methanol to protonate our alpha carbon. And we just finished doing an aldol. So what were the 3 steps in the aldol mechanism? In the base catalyze, deprotonate, and then attack, and then reprotonate. Deprotonate, attack, reprotonate. We see that pattern so many times. Okay, we did our aldol reaction. This was all an aldol. Okay, but we don't stop here because our product is perfectly set up to continue doing another attack. And here's where we need to recognize the new bond that's going to be formed is with the methyl group of the methylvinyl ketone. That's 1, 2, 3, 4, 5, 6 atoms away from the carbonyl of our initial enolate. So this is going to be our nucleophile number 2, if you will, electrophile number 2. And that's the bond we need to form. So how does that happen? I'm sorry, excuse me, I just realized we're about to do an aldol. That's because we just did a Michael addition. We did the conjugate addition to the alpha beta unsaturated carbonyl. It starts with the Michael, and now we do an aldol. So now we have the alpha carbon attacking a carbonyl. So how do we get started? Well, we get started the usual way. We deprotonate. Let's bring our base in again, methoxide. We deprotonate to make an enolate. And now, if you'd like, you can flip your enolate around so it's a little easier to see the 6-membered ring you're about to form. Here's our 1, 2, 3, 4 carbons still. Now we can see our nucleophile and our electrophile a little more clearly. The bond that you're about to form is right there. So we deprotonate, and now we attack. Enolate attacks the carbonyl. That's a classic aldol. And now we just formed a 6-membered ring, a new 6-membered ring. This is a double bond up here, a carbonyl. These are the 2 carbons that were just involved. And what does this carbon have on it? Single bond O minus. So what do we have to do to finish up? All we need to do is protonate. Can use our methanol again. And we're done. Well, we're almost done, I should say. Okay, we did our Michael. We did our aldol. And what's left? Well, this is not the typical product of a Robinson annulation. This is a beta-hydroxy carbonyl, but typically we get the cyclohexenone product out, so we have to lose water. So let me redraw this down here so we have some space for that mechanism. The last thing we want to do is we want to dehydrate. Okay, let's think back to that aldol when we wanted to dehydrate. How many steps was that? That was a two-step mechanism. We called that beta elimination. And how did it start? It starts like all these base catalyzed ones do. We're going to deprotonate alpha carbon. If you recognize the similarities to the patterns, that's really going to help. Deprotonate to form an enolate. Deprotonate to form an enolate, and then, so we could say step 1 is deprotonate. And then what does this enolate do? It sees that beta leaving group, so it reforms the carbonyl, kicks down the pi bond, kicks off that hydroxide leaving group. So step 2 is eject the beta leaving group. Now we have our Robinson product. We did a Michael first, and then we did an aldol with dehydration second. Quite a long mechanism, but if you could do the base catalyzed Robinson annulation mechanism, that means you really mastered all the various reactions that enols and enolates can undergo. Now let's talk about some advanced synthetic techniques that involve enols and enolates. There's one that involves stabilized enolates and a reaction known as a decarboxylation reaction. Okay, so let's do this decarboxylation reaction first. If you have a beta keto acid, so in other words a carboxylic acid that not in the alpha position but in the beta position, you have a carbonyl. We call that a beta keto acid for short. Turns out that when you heat these, they lose CO2. So you take this carbon dioxide group, this gets lost as CO2. This one carbon and 2 oxygen gets lost as CO2. And so your product, it's as if you just erased that functional group from there. The alpha carbon is still intact, but the extra carbon is gone. That's known as the decarboxylation reaction. This can be very useful to us synthetically. And we'll see examples of that. Now, how does this happen? The mechanism is a single-step concerted mechanism. It's an example of a pericyclic reaction. If we redraw our carboxylic acid like this, we can see a favorable 6-membered transition state here that can be formed. This carbonyl can come up and grab that proton, which can break that OH bond to form the pi bond and break this carbon-carbon bond. So ultimately, that's what you want to do, is you want to break that carbon-carbon bond. That's how you cleave off the molecule of carbon dioxide. So when we follow these arrows around, we end up with this product as one product and this product as another product. That's the result of that pericyclic step. And now let's think about what these products are. This guy is just carbon dioxide, drawn a little strange, but that's carbon dioxide, so we ejected that molecule. And what about this structure? How would you describe this functional group? It has an alcohol on the same carbon as a double bond. This is an enol. And what do we know enols do? They tautomerize very favorably to the corresponding ketone, which is the ketone that we're expecting in this reaction. Okay, so the mechanism is loss of CO2 followed by our two-step tautomerization mechanism is the complete mechanism. Now let me show you a reaction sequence where this is going to be useful to us. We can start with a substrate like this called diethylmalonate. If you treat this with a two-step process, sodium ethoxide and benzyl bromide, the first step you deprotonate to make the enolate. Okay, now remember this is a stabilized enolate because it has 2 electron withdrawing groups. We could use a weak base, a mild base like ethoxide to completely 100% deprotonate it, and that reaction goes well. This is very stable, and that means it's not only easy to make, it's also easy to use, and this alkylation reaction then is typically going to be pretty high yielding. So this we know that our enolate is a nucleophile, so when we add in our alkyl halide electrophile, we can get an SN2. We can do our alkylation reaction here. Okay, and we've seen this before doing an alpha alkylation, but here's the interesting part. If we take this species now and treat it with H3O plus heat, the H3O plus first does a hydrolysis it takes our ester groups and converts them to carboxylic acids. So we have addition, elimination of the water, we get a substitution. So we get this diacid out. And what happens when we heat this? Well, we have our beta carbonyl carboxylic acid pattern again. We have a carboxylic acid, and not in the alpha position, but in the beta position, we have a carbonyl. Now, in this case, it's not a ketone, it's another carboxylic acid, but that's okay. Any carbonyl will do. And then what happens is we eliminate one of these, one of those carboxylic acids. It's symmetrical, doesn't matter which one, but we eliminate one of them as carbon dioxide. So that here's our alpha carbon. Our alpha carbon still stays intact, but the CO2 group that used to be attached to the carboxylic acid group is now gone. So this overall sequence is pretty high yielding and goes pretty well. And so it turns out that this is a very useful strategy for synthesizing target molecules that look like this that might otherwise be difficult to achieve. So this diethyl malonate acts as if instead of, we know that one of these carbons, can be lost as CO2. So it reacts just like you had this enolate. If you had the acetic acid enolate, then you could make some very interesting molecules. Well, the diethyl malonate kind of gives you that structure because it gives you the two carbons with the alpha carbon having a negative charge, and this extra carbon, we add in that extra carbon to help stabilize this enolate. So it's added as an activating group that can later be removed, okay? And of course the ethoxy group is like a protector group for that OH and makes it more stable. So this is our acetic acid enolate equivalent. We describe these two as being synthetic equivalents. Anytime you want to use the acetic acid enolate, we'll use diethyl malonate instead. Okay, ethyl acetoacetate does the same thing. Remember, this group can be clipped off as lost as carbon dioxide. So this is a very nice reagent to use to be the acetone enolate equivalent. Because enolate of acetone is not so easy to use. It's very reactive. It's a pretty strong base, and so the yields in its reactions are not very high. So instead what we do is we add an ester group on here to act as an activating group to help stabilize the enolate intermediate, and then we have higher yielding reactions and we can remove that group and we're done. So let's look at an example where this might be useful. How about if I wanted to do the following transform? Let's make this carboxylic acid from this bromide. Okay, so it looks like we have, by comparing our starting material and our product, we see that this is a new carbon-carbon bond that we need to form because we just had these 5 carbons initially. So if I wanted to get these 2 carbons to come together, one of them must have been a nucleophile, one of them must have been an electrophile. This one is alpha to a carbonyl, so that makes it a very good, very reasonable nucleophile. So let's assume that this was my nucleophile, since it is an alpha carbon, which means this was my electrophile. And so if we do a retrosynthesis, remember, our retrosynthesis is asking what starting materials do I need? We need to plan this synthesis before we attempt doing this transform. And what we can do is we can go right back to just synthons. Let's just break that bond and put the positive charge here and a negative charge here. These are called synthons. And if we had these imaginary cation and anion, they would obviously come together to make this product. Well, so we can't buy the cyclopenyl carbocation, but that is the synthetic equivalent of having, let's say, a good leaving group on that carbon, which happens to be exactly what we have. So that would be a good electrophile that we already have. And to make this nucleophile, what we're going to use, instead of trying to deprotonate acetic acid, which would be impossible, we're going to use diethyl malonate. Okay, and so what the synthesis looks like then is we're going to use the anion, the enolate of diethyl malonate. So we'll treat this first, let's say, with some sodium methoxide to make the anion, then we'll throw in the alkyl halide. Okay, and this can do an SN2. We would expect that reaction to happen pretty well. With an enolate that would, or an ordinary enolate, that wouldn't work because this would do an elimination. But because this is more stable and less reactive, we can do this SN2. Okay, but how is this related to this compound? Well, we still see our 2 carbons, our 1,2 carbons. All we have to do is get rid of that, that extra carbon. So all we do is we H3O plus and heat. That's going to hydrolyze, and that's going to lose carbon dioxide. Now, in practical measures, it turns out that this saponification reaction of a hydrolysis of an ester usually works better with sodium hydroxide, with base. So probably what we would do is sodium hydroxide water to do the hydrolysis easier. And then step 2 is we can reprotonate to get the diacid, and it's the diacid that upon heat will do the decarboxylation reaction. So these are some advanced synthetic techniques involving enolates where we can use synthetic equivalents to make our enolates more easier to form and easier to handle in higher yielding reactions. Now there's another advanced synthetic topic, and that's dealing with enamines. This is another functional group that's related to enols and enolates, so this would be a good time to talk about it. Turns out these are also synthetic equivalents of enolate nucleophiles. So let's think about where an enamine comes from. First, let's recall if you have a ketone or an aldehyde and you react with a primary amine or ammonia and some kind of acid, you replace the CO double bond with a CN double bond. We call these imines when you have a CN double bond, and the reaction is, attack of the nitrogen nucleophile on the carbonyl, and then collapse of CTI to kick that water out. So overall, you're losing water in this reaction. And an imine, when you have a CN double bond and you treat it with H3O plus hydrolysis, this will revert back to the ketone and aldehyde, give you back the carbonyl, and free up that amino group. Okay, so we've seen this reaction before of a primary amine with a ketone or an aldehyde. Now, instead of a primary amine, if you use a secondary amine, then that is going to give a different product. When you react with a ketone, you're going to, again, replace the CO double bond with a CN double bond, but this product is now not going to be stable because that nitrogen has 4 bonds. It's going to be positively charged. So how can you stabilize this? Well, you can deprotonate one of these alpha protons, and that will get rid of the positive charge on nitrogen and give you a structure something like this, okay? This is known as an enamine because it's got an alkene, a carbon-carbon double bond, and amine on it. So kind of looks a little bit like an enol, right? Instead of having an oxygen here, we have a nitrogen, okay? But it's definitely related to that. And it's going to be related like an enol and an enolate in being nucleophilic. So first, let's just do an example of this. If we reacted this ketone with a secondary amine and some acid, this is tosic acid. It's just any old acid could be used here. Okay, what's going to happen is we're going to replace the CO double bond with a CN double bond. But that's not going to be our final product. We can't stop there. We need to neutralize this. But this is a case where we should think about where to deprotonate, which of these alpha protons would be better. And what we're going to do is we're going to want to go for this proton because that's going to give the more stable enamine product out. And so this is a feature of enamine chemistry, is you get the more stable structure out, known as the thermodynamic enol equivalent. Okay, so why would having a double bond here be more stable, be better than having a double bond here? Well, because it's conjugated now with the benzene ring. The benzene ring helps conjugate that. So we can conjugate the double bond to make it more stable. We can have more alkyl groups on there, more highly substituted, makes it more stable. Conjugated pi bond would be the major product here. Now, what can we do with an enamine? We're going to react it just like an enolate. So if we took this enamine that we just formed, this would be a nucleophile. So if we reacted it with a reactive electrophile like an alkyl halide, primary alkyl halide, or a methyl halide, for example, they're going to react. And where is an enolate or an enol reactive? It's at the alpha carbon, so right there is where it's going to be nucleophilic. How do we show that react? Well, analogous to an enol or an enolate, it's the lone pair that's going to come and form a pi bond. That's going to kick this pi bond out and attack whatever electrophile it is that we're going after. In this case, it's an alkyl group. We're doing an alpha alkylation. Oh, I'm sorry, we lost our pi bonds here. This was a benzene ring. We get the same product either way. But this would give us the following intermediate after we did this alpha alkylation. Okay, and this would not be stable. We would need to do something to stabilize this. And typically what we're going to do, if our methyl iodide was step 1, step 2, we're going to treat this with H3O+. And so rather than just neutralize it, we're going to do a hydrolysis that takes the CN double bond and turns it back into a CO double bond. So ultimately, if you remember, we started with this ketone. And so the transformation we did was to go from this ketone and alkylate at this position. Perhaps we could have done that using LDA, but depending on the ketone, depending on the substrates you're using, sometimes it's preferable instead to use the enamine, especially when you're trying to control regiochemistry. You could use the enamine as your nucleophile instead. And in fact, enamines kind of predated LDA, so this is a strategy that we could have used before LDA was an option for us to deprotonate and form the enolate. So let's see if we can do one more example here. We can take cyclopentanone and react it with this amine, the secondary amine. So after step 1, we're going to convert it to an enamine. So the nitrogen takes the place of the oxygen and we get a double bond. In this case, it doesn't matter which side it goes to. This is an enamine. This is a nucleophile. And so hopefully we're looking for some kind of electrophile now. Our electrophile in our second step is benzoyl chloride. So how can we bring those two together? Well, here's our alpha carbon. So we can have our lone pair come down and our pi bond come out. And then, do we lose the leaving group? No, we don't lose the leaving group. We break the pi bond and go up here. Remember, every time we attack a carbonyl, we break the pi bond. Okay, that kind of brings us to this complex structure here a little bit. And we have an acid chloride that we're reacting with. So what happens when we break that pi bond to the carbonyl? This intermediate's not very stable. This is most definitely a CTI, a charged tetrahedral intermediate, with a very good leaving group attached to the O-. So for sure, this oxygen is going to come back down, reform the carbonyl, and kick out that leaving group. So always with a with a acid chloride, we do addition elimination, we do substitution for that excellent leaving group. So that would be a way of installing this acyl group to the alpha carbon. That's pretty handy. And then our last step here, we're going to do hydrolysis. So an enamine is something that we create temporarily to use and activate it and make it like an enolate, and then we take that nitrogen back out. So that's what makes it a synthetic equivalent. So step 3, we're going to do hydrolysis. And hydrolysis of an imine gives us back our carbonyl. And that would be a very nice way of doing this transformation. Instead of using LDA and the very reactive enolate, we can use an enamine instead and do react it with an acid chloride electrophile in this case. That wraps it up for our second part of enols and enolates. Thanks very much.